So let's start. Let's continue with the rotation. So what we have talked about so far is the basic concepts of rotation and translation. So again, when we talk about the transformation, we talk about two steps: the rotation plus the translation. Translation means the positioning, or sometimes we call it offset. Okay, so it means that we have two frames, the rotation from one frame to the other, and also the translation means the position from one frame to the other. Okay, so far we have talked about the concepts of rotation. So today we will continue to talk about the calculation with some examples of rotation matrix. Okay, so for rotation, so far we talk about the 2D rotation matrix. So for example, if we have the rotation matrix R10, it means the rotation of frame 1 with respect to frame 0. So again, frame 0 is the reference. So to keep it consistent, I will call R10 because 0 is the reference. So it means R1 and with the reference of 0. Okay, so I will call it R10. So what is that? What is the rotation matrix R10? Again, here 0 is the base, or 0 is the reference. Okay, so if this is the reference, it means the R1 projected to the base, which is the reference 0. So then we can write it as x0, y0, x0, y0, because this is 2D, so this rotation matrix is going to have 4 terms. So the first term right here, because this is 1 projected to 0, so that is the first term is x1 dot product x0. And here we also write x1 dot product y0. Okay, we write the base and we write the base. Okay, so here is x1 and here is y1. So y1 projected to x0 and y1 projected to y0. Okay, so that is the 2D rotation matrix of R10. Again, 0 is the reference, so here we have x0, 0, 0, 0, and here have 1 and 1. That means 1 projected to 0 and 0, x0, y0 is the base. So how about R01? So if it's R01, now 1 is the reference. 1 is the reference. So if we want to write the rotation matrix of that, so 1 is the reference. So I have x1, y1, because this is the base, so I would like to write it first. This is the reference, so I write it first. x1, y1, x1, y1. And then now R0 projected to 1, so here I have x0 projected to 1 and y0, y0. So that is dot product. Okay, so previously last lecture we have covered the concepts of these dot product, projection, and unit vectors. Again, all of these x0, y0, x1, y1, they're all unit vectors. Okay, they're all unit vectors. And so far we have talked about the concepts and these for all these vectors and these rotation matrices. So let's continue with the calculation. And so a quick summarize of the properties. So for the properties, they're the same as transformation. Okay, so one property is that if we calculate the transpose of R10, it is equals to R01. So that is the commutative property of dot product. And also another thing which we have talked about it in the property of transformation, that is the orientation of frame 0 with respect to frame 1 is the inverse of the rotation of frame 1 with respect to frame 0. Okay? So remember in the transformation we have talked about, so if we calculate the transpose of one rotation matrix, it is equals to the inverse of the same rotation matrix. Okay? So there are some more properties. They're more about the orthogonal properties of these matrices. Okay, so a orthogonal matrix has a determinant of plus or minus 1. The set of all the orthogonal matrices with the determinant equals to 1 form the special orthogonal group, SON. So this is more about the matrix calculation. Okay, so now if we have 2, if n equals to 2 means it is 2D, and mean R is 2 times 2. So R is a matrix of 2 times 2. Okay, and the inverse of R is also belongs to 2 times 2 matrix. And the inverse of R equals to the transpose of R, as I just talked about it. Okay, and the columns and also the rows of R are orthogonal. And each column of R is a unit vector. Okay, so that is the properties. So then let's do one example. Okay, in this example, a two-dimensional rotation matrix corresponding to a rotation theta can be constructed by a rotation matrix for a rotation of minus theta. Okay, so what does it mean? So let's start from the beginning that if we do a 2D rotation, we do a 2D rotation, here I have my x0, y0. If we do a 2D rotation with theta, so for example, here I do a 2D rotation of theta, so here I have my x1 and y1 with a rotation of theta. Okay, so I rotate theta, so I have the new frame of x1, y1. Okay, so if we calculate the rotation matrix R10, again, what is that? That equals to the, because here 0 is the reference, so that here I have x0, y0, x0, y0, because that is the base of the projection, which is the reference. And here I have R1, so here must be x1 dot product and x1 dot product. And here is y1 dot product, y1 dot product. Okay, and then how we're going to calculate this rotation matrix? Again, we calculate it term by term. So the first term is x1 dot product x0. So if we calculate the dot product, it is x1, the absolute value of the vector, and again, all of these, they're all unit vectors. And the length or the absolute value of these unit vectors is 1, okay? Times cosine theta. Okay, so that is, again, I want to quickly review the dot product. Here we have a unit vector x0, here we have a unit vector x1, so the dot product equals to the length of x0 times the length of x1 times the theta in between, the angle in between, which is, we assume this is theta. Okay, so then we can quickly write down what is my R10 in this case. So then my R10, this term is 1 times cosine theta, because here I have my x1, here I have my x0, so the angle in between is theta, so it's cosine theta. The second term is x1 dot product of y0. Again, the length is 1, so that is 1 times cosine the angle. So let's see what is the angle between x1 and y0. Here I have my x1, here I have my y0. So the angle is 90 minus theta. Okay, so that should be cosine 90 minus theta. This term, the next term, is y1. Here is my y1, which is right here, my y1, and x0 is here. So this term should be 1 times cosine the angle, and the angle is theta plus 90, right? And the last term is y0 and y1, so the dot product of this term is 1 times cosine the angle, and the angle is theta. So that is cosine theta. Okay, so if we do a one more step calculation, there's going to be cosine theta, and this be cosine 90 minus theta, that is sine theta. And this term is negative sine theta. And this term is cosine theta. Okay, so I have my R10, that is pretty simple, which is this matrix. Okay, so then the question is asking, okay, so can be constructed by a rotation matrix for a rotation of negative theta. Negative theta means now instead of theta, I rotate negative theta. Okay, so it means if I rotate negative theta, then I can quickly write down this thing. So now I just replace the theta with negative theta. So I'll have cosine negative theta, negative sine negative theta, and this is going to be sine negative theta, and this is cosine negative theta. Okay, so now I'm just replace all these theta with negative theta. It means a rotation of negative theta. Okay, so then the thing can be simplified by cosine theta, the first term, and this is negative sine theta. And this term is negative is cancelled out, so that is sine theta. And the last term is cosine theta. Okay, so if we rotate negative theta, I will have this rotation matrix. And if we rotate theta, we will have this rotation matrix. Let's see this one and this one. What is the difference? What is the difference? And seems like this is just a transpose, right? The transpose of this one. So that is R10 transpose. And the transpose of that, based on the property we just talked about in the previous slide, that is R01. Okay, interesting. Okay, so it means that if we do a rotation, we do a inverse of the rotation with negative theta, it will just become the rotation from 1 to 0. Okay, So it makes sense, right? So here we have the base matrix x0 and y0. If we rotate it counterclockwise theta, it is equals to, we rotate from the x1, y1 to x0, y0 with negative theta, right? So this is what it means. Okay. So from 2D, let's go to 3D. So to 3D, I would say that every logic is the same. The only difference is that now instead of x and y, we have x, y, and z. Okay, so again, here, if we write it as R10, 0 is the reference. So then I write 0, 0, 0, which is the base, and the base, and the base, which is the reference, right? And we projected x1, y1, and z1 to the reference directly. Okay, so because this is 3D, so it is a matrix of 3 times 3. So it's also written as SO3. Okay. Again, now let me write R01. Okay. So now if 1 is the reference, how we're going to write it? 1 is the reference, so it is projected to 1, the frame 1. So I will have x1, y1, and z1. And this is x1, y1, and z1. And this is x1, y1, and z1. And the 0 is going to be x0, 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 and y0, 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 and y0, y0. Oh, sorry, this should be z0. z0, z0, and z0. And all of these, they're dot product. Okay? So let's do one example. So this example is a rotation of frame 0 is rotated to frame 1, and the question is to find the rotation matrix. Okay? So if frame 0 is rotated to frame 1, we're actually looking for R10. Okay, so if we want to calculate R10, again, I want to write the definition of R10, and my reference is 0, so I have my x0, y0, z0, and x0, y0, z0, and x0, y0, z0, and this thing is 1, so it means x projected to 0, x1 projected to 0, and y1 projected to 0, frame 0, and z1 projected to frame 0. Okay, again, this is a 3 times 3 matrix. So then, if we want to find the rotation matrix for this particular case, we need to calculate all these 9 terms. Okay, so let's start with the first one, x1 dot product x0. If we want to calculate x1 dot product x0, again, by definition, the dot product means the length of x1 times the length, the absolute value of x0, because they're all unit vectors. All of these are unit vectors, times cosine the theta. Okay, so in this case, let's find the theta between the unit vector x1 and unit vector x0. Where is my x1? Okay, so here I have my x1, and here I have my x0, and it seems like the angle in between is theta, so that is cosine theta. Okay, so again, these are unit vectors, so this is 1 and 1, so this is cosine theta. So the second term is x1 dot product y0, and obviously this is 1 times what is the angle? The angle is, where is my x1? Here is my x1, and here is my y0. So that is cosine 90 minus theta. Cosine 90 minus theta equals to sine theta. Next term, x1 times z0. Okay, because they're all unit vectors, and so it means the absolute value, the length of all these unit vectors is 1. So here just 1 times 1, so I will just directly goes to the cosine. Okay, so where is my x1? Here is my x1, and this is my z0. So the theta is, they're perpendicular to each other, so that is cosine 90. And again, that is 1 times cosine 90, and cosine 90 is 0. So here it goes to 0. Next term, x1 times y1 times x0. y1 times x0 is here, so this big angle is cosine is 1 times 1 times 1, so that is 1 times cosine 90 plus theta, which is from here to here. Okay, so that is negative sine theta. Next term, y1 times y0 dot product, y1 dot product y0, so that is 1 times cosine, here is my y1, here is my y0, so this is theta. Okay, so that is cosine theta, so this equals to cosine theta. Next term is y1, so next term is y1 z0. Here is my y1 and here is my z0, so this term should be 0. Okay, so y1 times z0 is cosine 90, so that is 0. And next term is z1 dot product x0. So here is my z1 and x0 is here, so that is perpendicular, so that is cosine 90. Again, it's 0. And next term is z1 dot product y0, so that is 1 times the cosine angle, so cosine, this is my z1 and this is my y0. Again, that is perpendicular, so that's cosine 90, so it's 0. And the last term is z1 dot product z0. Here is z1 and z0. Okay, so it seems like they share the same axis. So it is 1 times, they're the same axis, so it means the angle is 0, so that is cosine 0. Cosine 0 is 1, so it's 1 times 1, so this is 1. Okay, so now I have all the 9 terms calculated, so then this is going to be R10, and it equals to, I just have all my 9 terms arranged. So this first one is cosine theta, and this is sine theta, and this is 0, and this is negative sine theta, and this term is cosine theta, and this term is 0, and this term is 0 and 0 for this one, and the last one is 1. Okay, so for this example, my rotation matrix is like that. Okay, so then let's take a look at this example. So what is the action of this rotation from frame 0 to frame 1? Okay, so seems like if we take a look at over frame 0, here I have my z0, and here I have my x0, and here I have my y0. So what we're doing now is that we just use z, and we just use this thing, and we keep it the same, and we only rotate the plane x and y, right? And what we're doing is that we just rotate around z. Okay, so we rotate around z means we keep z and then we're just doing the rotation on the xy plane. By definition, if we have this type of rotation, if we do a rotation around z-axis with the theta, with the angle of theta, because in this case we just rotate theta, so we write it as r z theta. This particular matrix means the rotation around z-axis with the angle theta. Okay, so we need to remember all these basic rotation matrices. Later we will use that directly, and later for the sine and cosine we will shorten as c theta and s theta, just short for c. C means cosine and s means sine, because in the robotics analysis there could be a chain of these rotation matrices to simplify the writing, so we use c to represent cosine and s represent sine. So later we will see that. Okay, so here I want to emphasize that the rotation matrix RZ theta, it means we're doing the rotation around z-axis and we rotate theta. And so we have this format. Okay, so if we do Rx theta, it means we rotate around x-axis with the angle theta. And here, our y theta, it means we rotate around y-axis with the angle theta. And if we do the rotation around x-axis, and we will have this rotation matrix. Okay, and we need to remember that. And later we will use it directly. And then the ry theta, and we will have this basic rotation matrix. And again, all these three, we need to remember that. Okay, so RZ0, what does it mean? RZ0 means we rotate around z-axis with angle theta. It means we didn't do anything, right? We didn't rotate. We rotate 0 angle. Okay, and the thing equals to 1, 1, 1, and 0, 0, 0, 0, 0, 0. Okay. And there is another thing we need to remember, that is if we write multiplication, we write RZ theta, RZ phi, it means we rotate theta and we rotate phi, it equals to we rotate around z with the total angle of theta plus phi. It's easy to understand, right? It means if we do 2 steps of rotation with the angles of theta and phi, it equals to we do 1 step rotation with a larger angle of theta plus phi, because we're rotating around the same axis. If we rotate around the same axis, we can do that. Okay, so then we do one more example. And this example, we're not rotating around the same angle. Instead, we have the y0 and z1, they are on the same axis. Okay, so if we want to do that, and how we're going to do it from the definition. Okay, so the frame 0 is rotated to frame 1, and we need to find the rotation matrix. Again, we need to find R10. Okay, and then that is, again, we write all these terms. So here the reference 0, so I have x0, y0, z0, which is the reference, x0, y0, z0. This is because we're projecting x1, y1, and z1 to the 0 frame. Okay, so that's why we need to write the base first, which is the projection base. And then we project x1 to 0 frame, and y1 to 0 frame, and z1 to 0. Oh, sorry, this should be y. Okay, and z1 to z2 and dot product z0. Okay, and again, just to make it straightforward, and again we calculate each of these 9 terms. So because again all of these are unit vectors and we have done one example, so here I would like to just calculate the cosine of the angle, because anyway it is 1 times 1 times the cosine angle. Okay, so then I can write down the matrix, the calculation results directly. So the first term is x1 dot product x0, so that is 1 times the cosine theta, and the theta between these two unit vector is 45 degree. So that is cosine 45. Cosine 45 is square 2 over 2. Okay, and the next term is x1 dot product y0. Where is my x1? Here I have my x1 and y0. Okay, and y0 and z1, they're having the same axis. So if we consider what is happening here. So okay, so this is my 0 frame, right? This is my 0 frame. Okay, and my one frame, okay? So it seems like the xy plane of one frame is the same as xz plane of 0 frame, okay? So it means that they're going to be perpendicular to the axis y0 or the z1. Okay, so here I have my x1 and y0, and although in the figure we cannot really see that, but anyway, they share the same plane, and x1 and z1, they must be perpendicular to each other, so it must be perpendicular to y0. Okay, so it means here this is perpendicular. So if it is perpendicular, means it is cosine of the angle between x1 and y0, which is the unit vector. So this is 90, so this is cosine 90, so that is 0. Okay, the next term is x1. Here is my x1, and z0. Here is my z0, okay? So which is the angle between these two is this one, which is 45, which is 90 minus 45, so that's 45. So cosine 45 is square 2 over 2. Okay, the next term is y1. Here I have my y1 and my x0, okay? y1, x0. So again, this is 45, so it should be square 2 over 2. And the next is y1 dot product y0. Here I have my y1 and here I have my y0. y1 must be perpendicular to z1, so it must be perpendicular to y0. So cosine 90 is 0. And next is my y1 and z0. y1, and where is my z0? z0 is here, so that is 90 plus 45, that is 135. Cosine 135, that is minus square 2 over 2. And the last column, I have my z1. Here I have my z1, and z1 and x0, again, they're perpendicular, so cosine 90 is 90. And my z1 and y0, okay, so dot product z1 and y0 is 1 times cosine 0, right? Because they're the same axis, so the angle is 0. So cosine 0 is 1. And the last term is z1 dot product z0. Okay, and again, y1 or y0 must be perpendicular to z0, so z0 must be perpendicular to z1. The angle between these two is 90, so cosine 90 is 0. Okay, so we're all set. So I will stop here for the part 1.